Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we are going to discuss approximating integrals using interpolating polynomials. So in this topic, we will begin by reviewing the definition of the integral from a Riemann sum. We will then find different formulas that approximate the integral over an interval using only sampled data. And of course, that data will be periodically sampled. We will look at formulas that estimate the integral by evaluating or taking those data points that are both to the left and to the right of the interval in question, and then we will look at formulas that use only historic data points. In each case, we're going to find an interpolating polynomial, and we will integrate that interpolating polynomial over this last subinterval. In each case, we will see how the error is reduced as h gets smaller. That is, as the interval we are integrating over gets smaller. What we will then do is we will subdivide a larger interval of integration into subintervals and apply the formulas we've derived on each of these subintervals. These will be our composite integration formulas. We will finally give a discussion on the effect of discontinuities on the approximations we are making here. In the previous topic, we discussed how we can estimate the derivative of a function by first interpolating a number of points, finding the derivative of that interpolating polynomial, and determining what the slope of that interpolating polynomial is at the given point. What we're going to discuss now is integration. First, we're going to look at using Riemann sums, the definition you saw in first year that defines how we calculate the integral. Next, we will approximate integration by integrating interpolating polynomials instead. Finally, we will discuss how we can integrate over a longer interval. All right, now to compare methods, once again, instead of using a delta t, we will simply always use a step size h, whether or not we have a function of space where we generally have information both to the left and to the right of a point, or a function of time where we generally only have historic data. So we don't know what the value of the function is one time step into the future. Now, in approximating an integral, what we're going to do is we're going to be sampling points, either in space or time. Now, it's with these sampled points that we're going to estimate the integral of the underlying function on a particular interval. Now, you've already seen the original definition of the integral. On the right-hand side, we have a sum, which is called a Riemann sum, and the integral is defined as the limit as n goes to infinity, and h is the difference between the endpoints of the interval over n. Now, while this definition is correct, assuming the integral exists, it's not actually very efficient. The error term depends on the width of the interval times h times the derivative evaluated at some point all over 2. So it's not a very good approximation, as we're going to see, even for very small values of h or large values of n. All right, let's use the definition of the Riemann sum to approximate this integral going from 0 to 5 of e to the negative x cos of x. Now, the correct answer to the number of digits shown is seen below. If we use only 10 intervals for the Riemann sum, notice that, oh dear, we've got a relative error of almost 50%. That's not a really good approximation, although it calculated very quickly, less than 1 microsecond. Let's take 10 times as many points, or intervals. So now we are evaluating the function at 100 points, adding them up, multiplying by h, which is now smaller by a factor of 10, and notice that we're getting closer to the answer. In fact, if you take a look at the ratio of the errors, the error has gone down by a factor of 10. So we have significantly less error, but now it also takes approximately 10 times faster to longer to execute, as we're evaluating the function at 10 times as many points. Let's try 1,000. Okay, yeah, once again, the error has dropped by a factor of 10, and the time is increased by approximately a factor of 5. Now at 10,000 points, the error still continues to go down by a factor of 10, but once again, it takes 10 times longer to run. Here's 100,000 points, 1,000,000 points, 10 million points, and you're going to notice that at every single step, the error goes down by a factor of 10, and the time it requires to execute goes up by a factor of 10. There's 1 billion points, and this is now taking 15 seconds. This is now taking 2.5 minutes, and with 100 billion function evaluations, it now takes almost half an hour. However, notice what happened. With 10 billion points, we actually had 1, 2, 3, 4, 5, 6, 7, 8 digits of precision. However, with 100 billion points, we've only got one fewer, 7 digits of precision. The error actually went up by a factor of 5. This is once again a consequence of floating point numbers. We're adding lots and lots of numbers together, and the final result requires more precision than is offered by double precision floating point numbers. So it took us almost half an hour to calculate a worse answer. The balance of this topic is going to be looking at more efficient ways of estimating these integrals, so that, for example, if you are measuring current, you're measuring current, and you'd like to estimate the total number of coulombs that have passed over a period of time. Now in calculus, once again, you learned that the integral is the area under a curve. Suppose we have these 2 points, and we'd like to estimate the integral between them. Now, so we'd like to calculate that, and using the most primitive definition of the Riemann sum, we would simply calculate the area of this rectangle, and that area would estimate that integral. Now, of course, we could split it up, but assuming that we don't have any other information, that's the best approximation we have according to that first definition. However, instead, we have 2 points, so we can find an interpolating line that passes through those points. We could therefore integrate that interpolating line from the first point to the second, and that would give a better approximation of the area under the curve. Just as we did before, we're going to shift to 0. That is, from each of the x values, we will subtract x sub k. And because the distance between x values is h, we're left with the following. Now, the area under these 2 points is the same as the area under the original 2 points. Thus, the interpolating line can more easily be found, as seen here, and the integral is the integral of this interpolating straight line. Now from calculus, you know that the formula is this, and from this we may simplify the solution to be this expression. Basically, you'll notice that it's the average of the two values of the function times the width of the integral. All right, this is called the trapezoidal rule because we are essentially calculating the area of a trapezoid. All right, so now we have this approximation of the integral. Notice that this is the same as substituting x sub k minus 1 with x sub k minus h. So just to bring this closer to the way in which we defined or approximated the derivative. Now, what is the error of this? Well, calculating the error of this is much more difficult than calculating the error of, say, the derivative, because we're now integrating errors and that becomes much more detailed. However, it can be shown that the error of this is now negative 1/12 times the second derivative evaluated at some point times h cubed. This is actually a much better error than the previous approximation using the Reimann sum. Now let's convince ourselves that this calculation of the error is indeed correct. We're going to use a trapezoidal rule to estimate the integral of e to the negative x cos of x dx from 1 to 1 plus h for increasingly smaller values of h. Now this isn't really useful for calculating the integral because we're calculating different integrals each time. We're going to start by integrating from 1 to 1.5. And as you can see, the first approximation isn't that great with the trapezoidal rule. You can see that the error is approximately 10%. But more importantly, notice that the error is not that badly approximated by negative 1/12, the second derivative evaluated at 1, times our value of h all cubed. Let's estimate a smaller integral. Let's integrate from 1 to 1.25. All right, now there's the exact value. There's our approximation using the trapezoidal rule. And you'll notice that the error has dropped almost by a factor of 10. And if you calculate the new error over the previous error, you get that the ratio is 0.13. So yeah, almost a factor of 8. That's pretty good. If we now integrate from 1 to 1.125, so a even smaller interval, notice that the trapezoidal rule is giving us a better and better approximation. The error is going down significantly. It's now gone down by a factor of, again, 8. So that's pretty good again. And if you do this again with smaller and smaller intervals, you'll notice that with each time the error drops by a factor of 8. All right, and as you can see, the ratio does actually approach a factor of 8 with each iteration, and our approximation of the error is actually a good estimator of the actual error. So it seems as if the trapezoidal rule is pretty good at approximating the area under very small intervals. Now that's not going to be all that useful if we want to integrate from 1 to 2. But as long as we are using very small intervals, the trapezoidal rule seems to be pretty good. So can we find a better estimate of the integral than even the trapezoidal rule? Well, what should come to mind is interpolating polynomials. Let's take 3 points, the 3 points we see here, and let's find the interpolating quadratic between these 3 points. Now, you can do this yourself. Just shift the x values towards 0 by subtracting x sub k from each of them. You can find the interpolating quadratic and integrate that quadratic function from the shifted points being from negative h to positive h. If we then integrate that interpolating quadratic, we get this approximation here. Now, notice that we have a weighted average of the value of the function times the width of the new interval, which is now 2h. You can also show that the error is significantly smaller, at least if h is small. Now the error is order h to the 5th. Compare that to the previous error where the error was h to the 2 or h to the 1, h to the 3. All right, let's compare the 3 previous techniques for calculating the integral from xk minus 1 to xk plus 1. Now, for the Riemann sum, what we're going to do is we're going to apply the definition on just those 2 intervals. So we're going to sum up the 2 areas of these 2 rectangles. That gives us the following formula, and the error, if we do some extra calculations, is the result we see there. Notice that we have in the expression 2h, the width of the entire interval, times a weighted average of the 3 values of the function. Well, in fact, it's only a weighted average of 2 values of the function. All right, next, let's apply the trapezoidal rule. Now, what we'll do is we'll apply the trapezoidal rule to the first interval and to the second interval. Okay, that gives us 2 trapezoids. And if we sum up the area of those 2 trapezoids, we get that the formula is what we see here. And you'll notice again, it's the width of the interval, 2h, times a weighted average of the value of the function at those 3 points. Notice here that the error is now h cubed. Finally, the third rule we saw was Simpson's rule, which found an interpolating quadratic. That interpolating quadratic passed through those 3 points, and we integrated that interpolating quadratic. If we write that interpolating quadratic in the same form as the above 2, we see that again it's 2h times a weighted average of the 3 points. But notice now that the weights are not, in the first case, 0, 1/2, and 1/2. In the second case, 1/4, 1/2, 1/4. But now the 3 weights are 1/6, 2/3, 1/6. So it's weighted averages, but the third weighted average seems to be significantly better. And notice that the error is an expression times h to the 5. Let's compare these 3 methods. Let's look at a practical example. You know from calculus that the integral of sine from 0 to pi over 2 is 1. If we use the Riemann sum definition with 2 subintervals, we're essentially calculating the area of these 2 rectangles, and as you can see, the approximation of the integral significantly overestimates the value of the actual integral. The relative error is 34%. Next, let's calculate the area of these 2 trapezoids. If we calculate the area of these 2 trapezoids, it's a much better approximation with a relative error of only approximately 5%. So we went from a 34% relative error down to a 5% relative error. Okay. Next, let's use the third definition, Simpson's rule. Simpson's rule finds an interpolating quadratic between these 3 points and integrates it. That integral is equal to that value here, and you can see now the relative error is 0.2% approximately. So Simpson's rule is indeed significantly larger or better, even though the width of the interval is actually quite large. We went from a 33% relative error to a 0.2% relative error, or essentially the error dropped by a factor of 100. Well, more than 100. Now, one issue with Simpson's rule is that it requires us to have information about 2 time intervals, for example, or 2 spatial intervals. Can we find a better approximation with only 1 interval? So basically, can we find a better approximation of the integral from x sub k minus 1 to x sub k, but one that's better than the trapezoidal rule? Well, what we could do is take 4 points and find an interpolating cubic. All right, so now we have this interpolating cubic. What we can now do is integrate that interpolating cubic not over the entire interval, but on the interval in question. That is, we can find the area under the curve from x sub k minus 1 to x sub k in a similar way that the trapezoidal rule found the area under a straight line connecting those points. However, now we're integrating a cubic. So if you were to do what we've done before, shift towards the origin, integrate, you'd get the following formula. So the area under the interpolating cubic from x sub k minus 1 to x sub k is given by this expression. Notice it's a weighted average of the 4 values of the function at those 4 points. It's, however, not a convex combination because some of the coefficients are negative. Specifically, the coefficients of the first and last are negative 1 over 24. The error is approximately 11 over 720 times the fourth derivative times h to the 5. All right, that's not bad. Once again, we're going to approximate the integral from 1 to 1 plus h for successively smaller values of h. We have the exact value of the integral, which will change for each h, our approximation, the error of that approximation, our estimate of the error, and we will calculate the ratio between the current error over the previous error to see how much the error has dropped. So here's our first approximation, and already it's doing okay. We've already got at least 2 significant digits of precision in our answer. Dividing h by 2, well, notice that now we're doing even better. We seem to have 3 significant digits of precision at least. And you'll note that the error has gone down by 0.04. Next approximation, again, the error goes down, and the error is going down by 0.369. Now, we are assuming that as we are getting h smaller and smaller, the error should start dropping by a factor of 1 over 2 to the 5. So that's a half, quarter, an eighth, 16th, 32nd. So 0.0325. And so as we make h smaller, notice that yes, indeed, the error does indeed appear to be dropping by approximately 0.0325 with each step. All right, so we've already gotten a significantly better approximation using this formula than we saw previously with the trapezoidal rule. All right now, however, the approximation we just saw evaluates the function both at points prior to and after, or to the left and to the right, of the interval. What happens if we don't have information beyond the current point in time? We have the most recent datum, and that's it. Well, the obvious approach would be to integrate points prior to the current time. So we have 3 points here. We find an interpolating quadratic that passes through those 3 points, but we integrate that interpolating quadratic over the last interval. If we do that, we're not calculating Simpson's rule, but we're calculating Simpson's rule evaluated only on half of the interval. Now, this gives us the following approximation, and it's pretty good. It's an order h to the 4th approximation, not order h to the 5, and there are reasons for that, even though it's half of Simpson's rule. Mostly because with Simpson's rule, you get a balancing of the errors on either side of the central point. So this is an order h to the 4th approximation. Once again, let's approximate this integral from 1 to 1 plus h for successively smaller values of h. And once again, we have the exact value of the integral, the approximation using this formula, the error, our estimation of the error to give us confidence that the estimation of the error is correct, and the ratio of the current error over the previous error. So to start with, we have an okay approximation, as one may expect. And by dividing h by 2, we now integrate from 1 to 1.25. Once again, we see that the approximation gets better. In fact, it gets better by approximately 0.06. Now, 1 over 2 to the 4 is 0.0625, so that's pretty close. As we carry on, dividing h ever by smaller values, we do see that the error does get smaller with each approximation by a factor of 1 over 2 to the 4, approximately. And so we actually get a very good approximation. Not as good as the previous formula that evaluated points on both sides of the interval, but only worse by a factor of approximately 100. Okay, nice. Can we get an even better approximation? Sure, why not? Integrate the interpolating polynomial that goes through the current point and 3 previous points in history. Now, in that case, once again, we're only going to integrate this interpolating cubic on that last time interval. And here's the approximation. And this is an order h to the 5th approximation. So once again, let us approximate this integral for successively smaller values of h. So we're only integrating over one interval using this formula. Of course, we'll be evaluating the function to the left of this interval, which is assumed to be previous data. So we're still doing approximately as well as before. We start with almost two significant digits. Divide h by 2, the error seems to become less, and it's 0.022558. So the error has gone down by approximately 1 part in 40. Again, dividing h by 2, the error goes down. Each time we divide h by 2, the error continues to drop, and it's getting closer to dropping by a factor of 0.03125, which is 1 over 2 to the 5. So we're getting a reasonably good approximation of a very small integral. That last one isn't that good. We're probably already running into some of the issues with numerical approximations. All right, so now we have 4 formulas that approximate the integral over a single interval. The first two approximate the integral assuming that potentially data can be accessed on either side. The following 3, the first being the third, same as the third, this assumes that we only have data to the left of the most recent point. So once again, we see we have order h to the third, h to the fourth, and h to the fifth approximations. However, these only evaluate the integral over a potentially very small interval. But what happens if we want to integrate from, say, 0 to 10? We can't use any of these formulas because in that case, h is absolutely huge, which would mean that the error is probably actually quite significant. So we cannot use the one-step formulas for calculating larger integrals. So how do we integrate from 0 to the present? Now suppose, however, we're not integrating over a very small interval, but the only way to reduce the error is to reduce the value of h. Well, that's not going to work if we want to integrate from, say, 0 to 10. Instead, what we're going to do is we're going to divide the interval into n subintervals. So we'll pick an integer n positive, and h will be b minus a over n. We will then define x sub k to be the left-hand endpoint a plus k times h. Now that's all of these values, and each of these values are equally spaced. What we will now do is calculate the integral on each of these subintervals, or at least approximate the integral on each subinterval, and add them all up. So, well, by definition, these two should be equal. If we calculate the area under each of the curves on the subintervals, then the sum of those should be the entire integral from a to b. And of course, the same formula works if we're dealing with time. Thus, we can approximate the integral as follows. The integral from a to b, or x sub naught to xn, can be approximated by approximating the integral on each of the subintervals. So, for example, we could apply the trapezoidal rule to each subinterval as follows. So here we have the trapezoidal rule plus the error being applied to each of the n subintervals. Now, if we separate these two integrals, we have the following. All right, let's see if we can simplify these formulas. Now, let's take a look at the formula that approximates the integral. We have h times the sum of the average of the value of the function on at each of the endpoints. Now notice, however, that we have, for example, starting on the left, a half f at x naught plus a half x at x1. For the next subinterval, the approximation is a half x at x1 plus a half at f at x2. Now, if we sum up those two values, we get f at x1 in the middle. So basically, we are summing in totality h times a half f at x naught plus just adding up the value of f at each of the interior points from x1 to x sub n minus 1, and then finally adding a half f at xn, the other end point. All right, so that's a very simple formula that we can calculate. Evaluate the function at each of the points, multiply the first and the last function evaluations by 1/2, and add that to the sum of the balance of the entries and multiply by h. That gives us the area under that composition of trapezoids along that interval. How about the error? Well, we have to sum the errors on each of the subintervals. All right, now wait a second. Let's multiply by 1. So we're going to multiply by n over n. One of the n's we will bring out, and the 1 over n we will bring into the sum. Now notice now that we have therefore the average of the second derivatives evaluated at points between a and b. From the intermediate value theorem, you know that there is some point xi such that this average is equal to the second derivative evaluated at that point. But on the left-hand side, we have n times h cubed. The problem here is as n gets bigger, that's great, but how does that compare to h getting smaller? So if we have larger and larger number of subintervals, then n gets larger and larger, but h gets correspondingly smaller. So what's the total impact of n times h cubed? Well, you'll recall that h is equal to b minus a over n, so multiply both sides by n, and we get n times h is equal to b minus a. So we can simplify that error expression as follows. Negative b minus a times h squared all over 12 times the second derivative evaluated at some point xi that lies between a and b. Therefore, if we increase n, that makes h smaller, and consequently we get a better approximation. However, whereas the trapezoidal rule was order h cubed for a single interval, if we apply the trapezoidal rule many times, the error now is reduced to order h squared. We're going to see this over and over again. All right, let's implement this in C or C++. Here we have a function that integrates, and the error is big O of h squared, so that would be the name of this function. The first argument is a function pointer, the function we wish to integrate, and then we have the two endpoints a and b, followed by an unsigned integer n. The first thing we do is we calculate h. h is equal to b minus a over n, which is the width of each of the equal subintervals. For the sum, we will start by evaluating the function at a and b, summing them up and dividing by 2. We then have a loop that simply sums up the values of f evaluated at each of the interior points from x1 all the way up to x sub n minus 1. And then we just return the sum times h. So there's our composite trapezoidal rule implemented as a function in C or C++. All right, so once again, let's approximate the integral from 0 to 5 of e to the negative x cos of x dx using the composite trapezoidal rule. We will now use 2 to the n, or 2 to the k subintervals, starting with only 2. Now, we're going to calculate the approximation, the error. For the approximation of the error, I'm going to take the average value of the second derivative of that function from 0 to 5. And I will multiply that by h squared and times the width of the interval, which is 5. I will also calculate the ratio from the error, the current error over the previous error. All right, with 2 subintervals, well, as you might suspect, the error is reasonably large. It's not very good. It's about 50% relative error. However, even with 4 subintervals, we do significantly better. And the error is dropping, hey, by almost 1/4, which is what we were expecting. Double the number of intervals, halve h. A half h all squared is 1/4 h squared, so the error should drop by a factor of 4. Double the number of intervals again. Again, the error goes down, and it's going down by a factor of 4. We can continue doing this, and at each single step we do twice as many function evaluations, but the error also goes down by a factor of 4. Okay, and so with 1,000 subintervals, you'll notice that the error is approximately the same as the error was for the Reimann sum with 1,000,000 subintervals. So we have accomplished an accuracy with 1,000 subintervals, which results in 1,000 function evaluations, as compared to the Reimann sum definition, which saw us doing 1,000,000 function evaluations, and that took significantly more time. Well, actually, 1,000 times longer. So notice that we do have a significant number of digits that are equal. That's nice. Now instead, we could approximate the integral on each of the subintervals using the order h to the 5th centered approximation. So there's the formula for each of them plus the error term. And we can, of course, split the sum into 2 separate sums. The first sum is the approximation. The second sum is the error. Now, if you do a few extra calculations, you'll notice that there's a number of overlapping function evaluations. Consequently, we can calculate, instead of calculating the formula on each of the subintervals, we can just have a single formula for calculating the formula of all of those formulas summed. Okay, what does that mean? Well, we can factor out an h, but notice that we only ever once evaluate f at a minus h, or x sub -1. And its coefficient will be -1/24. We evaluate the function at the left-hand endpoint a, or x0, twice. Once it is -1/24, the second time it is 13/24. Summing those up gives us 12/24, or 1/2. Same for the next point, and interestingly enough, for all points between the point a plus 2h all the way to b minus 2h, we are just summing the value of the function. All right, and then we clean it up with the last few points. Now, this looks pretty close to the composite trapezoidal rule, except rather than just having a half evaluated at f at a and a half at f at b, we make small changes to evaluating the function at x sub or a minus h and a plus h, as well as b minus h and b plus h. So what's the effect? Well, the effect is that the error is significantly smaller. How much smaller? Well, here we have the sum of the errors. Performing the same operation we did before, multiplying by n over n, bringing 1 over n into the integral, we get this expression here. But remember that n times h is equal to b minus a, so I can change the n times h to the fifth to b minus a times h to the 4. Additionally, we have the average of the fourth derivative evaluated at points between a and b. So therefore, this simplifies to b minus a times h to the fourth times 11 over 720 times the fourth derivative evaluated at some point psi that lies between a and b. So if we have h, the error should go down by a factor of 2 to the 4, or a factor of 16. All right, let's implement this. So the error of this composite rule is order h to the 4. And notice that we again take a function pointer, the endpoints a and b, and an unsigned integer n as arguments. We calculate the value of h, and we initialize the sum with those 6 extraneous terms that don't follow the general pattern. So f at a minus h and b plus h have a multiplier of negative 1 over 24. F at a and f at b have a multiplier of 1/2, and f at a plus h and f at a minus h have a multiplier of 25 over 24. We then add all other entries into the sum and return sum times h. So once again, let's estimate the integral from 0 to 5 of e to the negative x times cos of x with more and more subintervals, starting with only 2. Already, the approximation of the error seems to be pretty good. With 4 subintervals, the error does drop, and it's dropping by approximately a factor of 20, a little bit less. Divide h by 2 again, or double the number of points. Again, the error drops. As we continue to do this, you will notice that the error drops by a factor of 1 over 2 to the 4, or approximately 0.0625. And so we're getting better and better approximations very quickly. So now we are approximating the integral with 1024 subintervals, and we have a very precise answer. Taking a look at this, we have 2, 4, 6, 8, 10 significant digits of accuracy. But more importantly, we have the same accuracy using this formula with 64 subintervals as we had with 1024 subintervals with the composite trapezoidal rule. So the small correction on either endpoint actually dealt with most of the error, which is quite remarkable. again assuming the function is sufficiently differentiable. Now, these functions that we've looked at so far assume that we can evaluate the function we're integrating at any point. So we can evaluate the function at a, at b, and at any point in between. The backwards formulas are only going to be used when we're trying to dynamically approximate the value of the integral in real time, where all we have access to is historic data. That is the current data point and previous data points that are sampled periodically. So how would you implement this in an embedded system? Well, at time t equals 0, you have an appropriate variable that's initialized to 0. Then, with every single subsequent time step, you have a new value, and assuming you're storing a sufficient number of the previous values, you can then approximate the integral over this last time step. You can then add this approximation to the variable that we initialized. And you can use whichever formula you want, but in the end, at each single step, we will have an approximation that looks like this if we're using the trapezoidal rule on each subinterval, or the integral of the quadratic interpolating polynomial over the last subinterval, or the integral of the interpolating cubic, and again integrating that only over the last subinterval. So we would, with every single step, perform this calculation and add it to our running sum that should therefore store an approximate value of the integral of the function. All right, we've now seen various different ways of approximating the value of an integral. Now, suppose that we are measuring current or voltage, but at this point a switch is being flipped. Now, a switch means that we are going from zero current to a significant non-zero current almost instantaneously, or the same with voltage, say going from 0 to 5 volts or from 5 volts to 0. This is essentially going to be a discontinuity in what we are integrating. But if there's a discontinuity, that means that the function is no longer differentiable at that point, and consequently all of our approximations are nonsense because we require the function to be at least twice differentiable. So for example, here we have a situation where the current is 0 milliamps initially, but sometime in the last millisecond a switch was flipped and we've jumped from 0 milliamps to 24 milliamps. Now, what is the integral of this current over this subinterval? Well, the total charge that passes this point could be anywhere between 0 microcoulombs if the switch is thrown at the very last possible moment between the last sample and the current sample. So maybe a split second before we take our most current reading. Alternatively, if the switch was thrown very close to 1 millisecond in the past, we could already have 24 microcoulombs that have passed this point in the circuit in the last millisecond. So we have a huge possible range of values. Which do we pick? Well, we can't pick any because we don't know anything about the system. It's a discontinuity. You don't know where in that time interval a switch was flipped if all you're doing is reading the current passing through a point periodically, once per millisecond. So the correct answer is somewhere between 0 microcoulombs and 24 microcoulombs. Let's consider the three algorithms we saw. If we apply just the trapezoidal rule on this subinterval, then we get an approximation of 12 millicoulombs, which is about as good as we can do. It's as close to the it is the midpoint. If we take the formula where we integrated from a quadratic passing through 3 points and integrated over the last time interval, then we get an approximation of 10 microcoulombs, which is suboptimal. It's no longer near the center. And if we found the interpolating cubic, integrating it over the last time interval, we get an even worse approximation because, once again, if we have no better information, we had best assume the midpoint. So what this suggests is, if there's actually a discontinuity, our best bet is not the most accurate formula, but rather the trapezoidal rule. So we still have a huge error here, but the trapezoidal rule gives us the best possible approximation. So what we would do in reality is, let's say you notice that a switch is flipped, meaning that there's going to be a very large change in whatever is being read. You could then set a flag to indicate that a discontinuity is expected. If a discontinuity is expected in the last time cycle, then you use the trapezoidal rule for one step. For all subsequent steps, you would then revert to using probably a more accurate technique. All right, following this topic, you are now aware that there are numerous ways that we can approximate the integral over a single interval. And you have seen that we can use, for example, the trapezoidal rule, which integrated an interpolating line between 2 points. And we also saw a centered order h to the 5th rule that saw us finding an interpolating cubic between 4 points and integrating that cubic between the two centered points. That gave us a much more accurate approximation of the integral on that subinterval. You also understand that we found formulas that can approximate an integral over a given interval using only historic data, that is the last data point and any previous data that we have on record. If we have only 2 points on record, we can use the trapezoidal rule. However, we've also seen 2 other formulas where we use an interpolating quadratic between the last 3 points and an interpolating cubic between the last 4 points. In each of the cases, we integrated only over the last subinterval. After all, that is what we are interested in. What has happened since the last time sample? You are aware of how we can compose these approximations to find good approximations of the integral over larger intervals. And you've actually seen that all of these formulas work as promised by looking at a specific example and dividing the h value in each case to see better and better approximations. However, at the end, you also understand that discontinuities in our functions will result in very large errors. We can no longer use the higher order approximations because they assume continuity. Consequently, if we have a discontinuity in the last time interval, it makes sense that we revert to the simplest trapezoidal rule to best approximate the integral over the last time period. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!